Hello, my name is Tyler Morency. I'm content manager here at Measurand. Thanks for tuning in to this virtual roundtable discussion today. I'm joined by my colleague, Christian Levesque, as well as Andy Take and Neil Hoult from Queen's University to share and discuss some of the NSERC funded research that they're doing in regards to rail track deformation monitoring. Hi, everybody.
Hi.
Hello.
Hello. Yeah, I would love if we could just go around and we can tell everybody a little bit about ourselves.
I'll give it a start. Hi, I'm Christiane Levesque. All of you, most of you will know me here. I've been at Measurand for 9, almost 10 years, and am currently the Director of Research. In my time at Measurand, I've covered a lot of different roles, from support and sales through to now the Director of Research, all that time having done some work in the product development work. That's me. Andy, do you mind taking the next?
Yeah, I'm Andy Take. I'm professor in Canada Research Chair at Queen's University. My team here does work on landslide processes as well as instrumentation and monitoring.
Excellent.
And my name is Neil Hoult. I'm also a professor at Queen's University in the Department of Civil Engineering, and my research interests fit broadly under the umbrella of monitoring, be it bridge structures, tunnels, and my work with Andy falls a lot into the area of rail track monitoring, looking at various issues to do with degradation and repair of rail track systems.
Thank you very much. So I think we should just jump right into it. So your team conducted a field evaluation of the ShapeArray system to measure rail deformation. Can you tell us a little bit more about how you selected a site for monitoring and why?
Yeah, sure thing. So we worked with a rail owner who had a spur line going to a factory that had 2 trains a day, one empty and one heavily loaded. And that particular track was limited to 16 kilometers an hour due to the issues with maintaining track geometry on that particular length of track. In particularly, what they found was localized soft spots, and these typically were between 20 and 25 meters in length, where you had a displacement bowl forming. And they found that they had to reballast at least 3 times per year to maintain track geometry. And so this was a significant maintenance issue for them. The geotechnical profile at this particular site is on average about 3/4 of a meter of ballast, followed by a meter of sand with gravel and silt. And then finally, all of that sitting on a clay subgrade. So this is a fascinating site in terms of unknown geotechnical problem and issues that in practice look like this. And so clearly you can see from the vertical degradation of track geometry, there's some massive issues here. You can also see the variation in ballast color, sort of indicating where they have had to reballast. And so this enabled us to ask some really fascinating questions. We wanted to find out, what is the mechanism behind these soft spots? Does the displacement bowl simply deepen, or does it expand along the length of the rail? So does the dynamic loading essentially make these soft spots expand with time? We wanted to know why they grow, and in particular, look at the influence of climate on that and the seasonal availability of moisture. And then finally, we wanted to think about if we wanted to fix this issue. There's a variety of different remediation schemes that could be used, but how do we quantify how well one of these schemes worked? So all of these questions, we need a new sensor we need a new technology to help us monitor that, to try and capture that spatial distribution, i.e. the profile along the length of the rail, as well as the temporal aspects, the seasonality of the deformation. And so we chose this particular section because it had a very known problem and a wide range of displacements, and a section of track that they knew they had to fix.
And the new sensor that you mentioned, can you talk, Neil, how you came to evaluate and choose ShapeArray as a instrument that showed some promise for this application?
Yeah, so as we see in this slide, a ShapeArray is a great technology in that it's a series of rigid stainless steel segments linked together with flexible joints, and through the use of MEMS or microelectrical mechanical system sensors, basically each rigid unit is able to figure out what angle it's at, similar to the technology in your cell phone that allows you to figure out whether your cell phone is oriented in portrait or landscape. And so you can get the angle of each segment, and then if you multiply the angle by the length of the segment, you can get a measurement of the displacement of each end of the segment relative to each other. And as you can see in the slide, these units are linked together. So if you can figure out how much one unit is displaced, you can add that to the next, And in the next slide, we can see how that would work for our particular application. So assuming that the ends of our ShapeArray were fixed and not displacing at all, then the segments in between are going to rotate at a certain angle. We're going to take that angle, multiply it by the length, and figure out the displacement of each one of those segments to be able to get a sense of what the displacement bowl looks like in this case. And then in practical terms, looking at the next slide, you can see that the unit can be affixed to the ties of the rail track segment. In the picture, you can see that it's actually been put into a conduit, so you can't actually see the flexible joints between the various units. That's to protect the measurement equipment from passing trains. You can also see in the background we have a data logging system that I'll talk about in greater detail in the next slide. And so basically what we're able to do is we're able to look at two 40-meter long ShapeArrays that allow us to see the full deformation picture of that settlement bowl. As I say, we place them in steel conduits, 3.05 meters long, 39 millimeter outer diameter, simply to protect the sensitive measurement equipment inside. Attach them to the size. You can see we attach them every third tie using C-clips, and then we monitored them every hour using a Campbell Scientific data logger that was actually hooked up to a solar panel, enabling us to do this remotely, and then also hooked up to a cell phone modem, which then allowed us to gain access to the data every day so that we could continuously update our picture of the displacement profile, which really allowed us in a way that would not be possible with typical either rail vehicle mounted systems or other technologies to get an ongoing picture of what the settlement bowl development looked like.
Before we move on, I'm just curious as to the decision to install the ShapeArray onto the side of the track rather than maybe down the center line of the railway.
Yeah, so I mean that was an issue that we suspected we might find, and that is the two rails were actually settling at a different rate. So there was actually some twist to the amount of the settlement, and so we put ShapeArrays on both the east and west rails, as we referred to them, in order to be able to capture whether that displacement bowl was actually uniform or whether there was some differential element to the displacement bowl. And as we'll see in some later results, that was definitely a wise decision because there was a differential mechanism going on there that we were able to, again, capture because of the nature of the ShapeArray.
Perfect. And so, Andy, whenever you're trying a kind of novel technique or instrumentation method, part of establishing its results and verifying it is applying it against conventional measurement to establish a baseline. And so I'm curious as to how you measure track deflection to assess the instrument's accuracy. And why did you choose this for the ground truth baseline?
Yeah. I'll go back to this previous picture that we showed earlier. And this one shows a ferro laser scanner, so a Lidar system, along with some spherical targets. And so we chose Lidar to give us as much sort of detail as we possibly could in terms of point cloud density. So we set up the Lidar for most of the setups. We set it in between the two rails. And looking at the data from a top-down perspective, what that enabled us to do is with 5 different Lidar positions get a really incredibly detailed view of the track embankment, as well as the positions of the rails. And so in the middle of this, you'll see a section A dashed with an electrical transmission tower. We use that as our elevation reference. And so if I show you what that data looks like through that particular cross section, there's our electrical pylon or electrical transmission tower. And over in the far at the right of this, at a y coordinate of y equals 0, we can see the track and the relatively small embankment. Not a very big embankment. We can see it's steeper on one side than the other. And if we zoom in even more at this Lidar data, this is the kind of data we wanted to get. So we wanted data so that we could get the elevation of the tie, so that those are the lowest returns of the laser pulses. You notice that there's lots of ballast sitting on top of that, so we did a linear regression to the lowest returns of the laser points. We only see the inside of the rail because the outside of the rail is occluded. There's no line of sight to the terrestrial laser scanner, but that enables us to measure the rail elevations independently, and we can choose to do that every half meter, every meter if we want, and we can also obtain the tie elevation. The other thing we wanted to do with Lidar is to get a sense of what the ballast is doing. Look at the ditching, see if there's anything going on there. So Lidar is really great technology, very, very in-depth point clouds, especially when you run them at this particular resolution. The downside is the temporal resolution. This took us all day to do a laser scan, and obviously you can't do this in areas where you have a lot of train traffic. So we chose this particular site because we had a big enough window to do these laser scans, and we could do them a few times through the length of the project to have different waypoints in time that we could compare to the ShapeArray data.
And so, Neil, what did you learn from this comparison?
Yeah, so a couple of things. So first of all, here we see a layout along the rail of our Lidar data versus our ShapeArray data. And the first thing to note is that what we did with the data is we aligned it at both ends. And there's a couple of reasons for that. One is that we weren't too concerned with whether the track was on a slope or not. That's not really an issue in terms of operating the railway. It's really a question of if there's any differential change in elevation. That's what the provider cares about. And so as a result, what we did was we basically assumed both ends of the rail were horizontal. And then the other thing we did was we compared the Lidar data to the ShapeArray data in this graph. So on your y-axis is displacement, and again on your x-axis is rail length. And what we see is a very good comparison, where we're getting, largely speaking, the same results from both measurement systems. If anything, you could say that the Lidar had a few more glitches along the way, and that's because the Lidar system provides you with this point cloud of data, but you don't get to pick where those points are going to be. It has to do with the system, how it just reflects light off objects. And so as a result, some of the points that we selected as being on the railhead didn't actually turn out to be on the railhead. And so you see in the graph a couple stray LiDAR points that don't seem to match, and that's more a challenge of the LiDAR system than the ShapeArray. You see with the ShapeArray, we're getting a very consistent bowl shape, and even after just a month of monitoring, we're picking up displacements of about 10 millimeters. And then if we go to the next slide, we can see the sorts of results we can get after 8 months of monitoring. So again, very consistent results between the LiDAR and the ShapeArray. Again, the occasional LiDAR point gone astray. But we can see that the data from both sets of monitoring systems are within 7 millimeters, and we can see the advantage of the ShapeArray system in terms of capturing that overall display shape, and to be able to do it over the course of the entire monitoring period, whereas with the LiDAR system, we were coming in and going out. So we have occasional LiDAR readings, but again, because we had this data logger with solar panel on site with cell modem, we're getting hourly updates about what the movement of the track is, and again, with very good agreement with the LiDAR system.
So I guess getting these two comparisons together, what was the most helpful information that you received from the data, or talk about maybe the difference in kind of temporal resolution?
Yeah, so there's two bits of helpful information. One we see on the next slide is the cross-level information that we were able to get from the ShapeArray. So you asked me earlier, Tyler, about why did we put ShapeArray on either rail, and it was because we felt that there might be differential settlement between the two rails, and indeed there was. And what we were able to do was to take the two displacement bowls from the ShapeArray and subtract them from one another to get an idea of the change in cross level, which in railway speak is basically just, are the two rails at an angle to one another? And so we see in the illustration in the figure that a negative value indicates, in our case, that the west rail is below the east rail, and a positive value would indicate that the west rail was above the east rail. And so we can see that over the entire length we monitored, it was always a question of the west rail falling below the east rail, upwards of 40 millimeters potential cross-level change. Fortunately for this particular rail track, the allowable amount is 75 millimeters in terms of and so that wasn't so bad. But again, a nice thing coming out of the ShapeArray was the ability to capture that. But also, as we see on the next slide, we also have the ability, because we're logging continuously every hour, to see how the results are changing with time. So here we have the displacement bowl profiles from August 24th, when we started the monitoring in 2018, right the way through to March 24th in 2019, and we can see how that displacement was developing. This is one way to look at this, but another way to look at it on the next slide is to pick a spot where the displacement is a maximum and track that maximum displacement over time. So in this case, we have on our y-axis the rate of displacement calculated as what the change in displacement per year would be. And then on the bottom, we have the date at which we're capturing that rate of displacement. And so we can really see how that rate of displacement is evolving, starting with early fall, when it's not, well, to be honest, all these rates of displacement are fairly high for a rail track, but it's kind of at its lowest in the early fall. And then we get to the late fall, and we can see that the amount of displacement per year we would be getting is almost at its highest. Then it actually slows down a bit for the winter. And we think this is because of ground freezing. So the ground is stiffening up a bit, resisting this development of the displacement bowl. And then we get to the spring, where things start to thaw out, and our displacement rate is at its highest. And again, this is possible because of the ShapeArray data. You couldn't do this with the Lidar data. You couldn't possibly come to site frequently enough to be able to get data, whereas with the ShapeArray, we were able to get it easily and really understand how this displacement bowl was developing in order to tell the rail operator the extent of their problem and also the time history behind their problem, which I think is a real plus point of the ShapeArray technology.
So I'm going to ask the same question to you, Andy. What did you glean from this?
Yeah, so it sort of falls on from that time rate of settlement, and it gives us a glimpse of the failure mechanism. And so if this is what the track looked like after the end of that deformation, before they picked up the rail and rebalanced the track. If I were just looking at that, I would have thought, my first gut feeling is that, whoa, there's lateral and vertical displacement. That is like a bearing capacity, single-sided or asymmetric bearing capacity style mechanism. And I bet there was a bearing capacity failure. And if I just had the Lidar data, so here we're taking a cross section showing that in this particular case, we had about 100 millimeters of vertical and about 80 millimeters of lateral displacement. We see some sort of bulging, and so you could imagine that we could draw, if we wanted to, some sort of bearing capacity surface here. If we only had the Lidar data, I would be tempted to think that that was a single failure event. But what we've learned from this, in this particular failure mechanism, in the high temporal resolution of the ShapeArray, is that this sort of sideways failure is the accumulation of plastic or irrecoverable displacement with time. This didn't just happen one day. Instead, it happened with little contributions each and every day, and those contributions and the magnitude of them related to the seasonal availability of moisture. And so for me, what that does is it gives us an indication of how better to try and mitigate these particular types of failures.
It's really interesting to see how the two methods of data collection can tell two kind of really different stories.
Yeah, you bet. And so what we get from the Lidar in this particular case is the confirmation of bulging on this graph on the right-hand side and not on the left-hand side. You can see some subtle differences in vegetation, as you'd expect from different times of year or different years. But yeah, the combination of these data sets is really powerful. In particularly, the fact that we can get results every hour was a huge benefit to us.
Yeah. Especially like determining those kind of or theorizing about those gradual processes that take place and not being able to observe that that phenomenon otherwise. Christian, I was wondering if you had any kind of reflections or observations.
I do actually. I've been watching along for a while on this particular research project. What we did is essentially do a meeting almost every other week where we go through the data with Andy and Robing, who was the master's student who was working on this particular project. So I've seen quite a bit, but even with seeing all that information, I always find out slightly new pieces of information every time we talk. So I do have a couple of questions. You mentioned that this was really very helpful for better understanding the mechanisms that came out or have been at work for this type of piece. And I know that you've been working with ShapeArray before, Andy. I'm wondering, would you find it to be more helpful? Like most of the time people are looking at ShapeArrays more as a monitoring tool in terms of we got construction monitoring and things of that sort. Would you think that it would be more helpful in maybe some preliminary problem solving side of things, investigation side? as well?
Yeah, certainly. I think it's thinking about how to remediate this site. I think the more we know about how the behavior of the problem, the more we know about the problem we're trying to fix, the better we're going to fix it. We will pick our remediation scheme for railways, for example, to better address them. And in thinking about other applications for ShapeArray on rail, so here we have a sort of bearing capacity style failure. If this were a steeper slope and a landslide, even if we primarily, with the ShapeArray, we primarily measure the vertical component of deflection, we would pick up both that, we would pick up the fact that the track is moving from that, even though if we have, like in this particular case, a combination of motion of vertical and lateral. And so from a monitoring of landslides point of view, or in terms of monitoring for third-party intervention, let's say a pipeline is being HDD underneath the track, and the railway owner wants to ensure that displacements are kept within a certain tolerance. I mean, the first question I would have is, well, how much is the track moving before the pipeline comes along? And so it's, being able to answer that question, as well as what's happening when the directional drilling occurs, I think would be a really valuable combination of data.
Yeah, I would agree with that. Neil, I have a question for you as well. When you were talking about the cross-level data, you showed us a really nice graph for it. I had a question about how often would somebody potentially be able to look at that data? Because you mentioned that we're getting the data fairly quickly. Is this something that could be essentially automated, so that if they understood it over time, say looking at it on a weekly basis, for example, a report, so that you can sort of see what's going on, is that something that you think would have been useful for the track owner in this case?
Oh, absolutely. I think it is definitely possible to, because we're able to acquire the data on a daily basis, with computer software, you could easily write a code that would show you rates, show you increases. You could set thresholds, so you could even automate it so that the infrastructure owner didn't even necessarily need to look at the data on a daily basis or a weekly basis. They could set it up so that a threshold would tell them that they had a problem. So, a simple text message to their cell phone to indicate that the cross level in that case had crossed a certain threshold, the 76 millimeters that represents the unacceptable level for cross level, and then they could know that they needed to do something about it, or they could set it at a lower level so that they could take action ahead of crossing any sort of critical level. So absolutely, this data could definitely be set up to report or be used for an automated detection system, and it's easy to do once you have that remote data logging system in place.
Excellent. And I have another probably more generalized question that either one of you could probably help me out with. My experience is mostly in submarine landslides. So when we were looking at everything, we were talking about multi-beam bathymetry. So it's similar kind of idea as what you have with Lidar, where you have a cloud of points. But in our case, we would have to actually then go through and do a lot of work to reduce the data and turn it into an actual grid of points that made sense. And I was curious with Lidar, I know it's probably moved along a lot since I was looking at multi-beam forever ago now. How much time would it take to actually do the data processing on that particular piece of equipment? Is that something that would be fairly quickly done, like in a day? Because you mentioned taking the readings as a day. Would it be just in another day, or is it something that takes much longer to get the information from?
Yeah, so it's quite a lengthy workflow. So you have to register. We use the spheres in the field, and we leapfrog the spheres. And the purpose of those spheres are to enable us to do automatic point cloud registration. So from between each setup of the terrestrial laser scanner, because we wanted to measure the precise location of the railhead, we ran it at a very high resolution. And so that means millions and millions of data points from each section registered into the same coordinate system. And then there is the workflow of finding the railhead in that cloud of points and selecting the points only on top of the railhead in 3D space with time. So it is a great data set, but the workflow is enormous and certainly potential and possible for automation, but certainly it's a daunting task.
What other kind of instrumentation would you have considered to get other kinds of data sets to tell different stories?
So the other data that we collected, but we ended up not using, was total station survey of the railhead. And so in that particular case, we had students, one student on the total station and another student with the prism pole walking along the rail, and above every tie, taking a point of the tie and the rail. And the inherent ability to hold the pole straight, in theory, you should be able to get within a millimeter, but what we found is that the Lidar data was a lot more consistent and a lot better data to serve as a baseline, and so we didn't use that total station data, and it took a full day of two people doing that detailed level of total station surveying. And this is on a track where we had a period of time where we could have possession of the track that was hours and hours long. If this were a railway where we didn't have that due to traffic concerns, obviously you can't do that under mainline rail.
Yeah, that doesn't sound feasible.
No.
And it is very interesting that there's the margin of error in taking the readings and sampling that data is a factor that has to be considered. The next question that I had was, what does this mean for rail line operators and owners, and is takeaway from this research?
What this gives us is, one thing it gives us is the ability to look and actually quantify how well remediation schemes work. Do you want to explain some of our upcoming work on that, Neil?
Yeah, so one of the challenges always with rail remediation is knowing whether what you've done is actually solve the problem. And so what you can do with the ShapeArray is you can put it on ahead of time to get a sense of what your problem is, what the rate is, whether it's seasonally affected. Then you can come in and do the remediation. So there are a number of different products available, and we're actually looking to do some research on helical pile remediation techniques in the near future. And then afterwards, you come in, you reinstall your ShapeArray after the work has been done, and you're able to monitor again the rate of displacement, the rate of change, to see if the rehabilitation has actually solved your problem, or at least reduce the impact of your problem to a more manageable amount, so that you don't have to come and reballast every couple months. Because really what you're hoping to do with all these things is decrease the cost of maintenance for the rail operator and ensure that safety is maintained. And so it's really exciting to be able to use these technologies to figure out, really oftentimes for the first time, whether these rail rehabilitation techniques are doing what they say on the box, because it has been a challenge to this point to get this sort of data along the length of the rail with temporal resolution that allows you to really see the impact of it at a not too prohibitive cost. So obviously there are a number of things you can do to monitor a site, from strain gauges to piezometers to all sorts of, you could throw the kitchen sink at a site like this, but the costs then become prohibitive. The installation times become difficult, and it really isn't advantageous for a rail operator to do. Whereas this, with the quick installation and the ready access to the data, really makes the ShapeArray an appealing choice for looking at these sorts of rail degradation problems.
Now you mentioned really quick, just to interject here, Neil, that you found it to be an interesting choice for the remediation, and you mentioned that you're planning to do the remediation soon. Is that something that you're planning to present in the future as well?
Absolutely, yeah. No, we're keen to look at how we're able to use the ShapeArray to monitor both pre and post rehabilitation work at sites. And so, yeah, we'll definitely be in the not too distant future producing work, both presentations and papers, to show how the ShapeArray can be used to track the effectiveness of the rehabilitation work at sites like this.
Thank you very, very much for being able to speak with us and share this interesting work.
Thank you. It was a great chance, and we really enjoyed this research project.